I am here to talk mostly about DaVinci for you today, but given that this is a course also, and I thought I might tell a little bit of my story of how I got to be where I am, which right now is a mix of management and science leadership on this discovery mission that will take us back to Venus in a few years. Chris covered some of this, but I thought I'd share just for completeness that I grew up in South Florida. If you all have been there, I'm real close to the Sawgrass Mills Mall, which was a major place to be for a teenager in Sunrise. I loved all subjects and some other activities that I'm showing here. I ended up, thinking about going out of state for college, but decided that the scholarships were too good to pass up. And so I stayed in Florida at University of Florida for 7.5 years, as it turns out, including my PhD. And I was in physics for most of the time, but I started out as an English major because I do love writing. Luckily, there's a lot of writing in science, so I ended up not being too disappointed with my chosen career path. I also found my way to physics with the intention of acing the MCAT on my way to medical school to be a surgeon. So I went through a couple of iterations on what I was going to be when I grew up, but I ended up sticking with physics, and it's been a really good decision because it's really given me a lot of opportunity, a lot of fundamental skills that have served me very well in this trajectory of my career. Chris mentioned I did a postdoc at the University of Maryland College Park. That is also when I purchased my first winter coat to move to Maryland. I had to drive 2 hours to find one in Florida, but I found one and I moved up there. And I did a physics postdoc, a lot of collaborations with the chemistry department. So continued that interdisciplinary flavor of the work that I did and really enjoyed that. And then I've been serving NASA since 2004 at NASA Goddard Space Flight Center, that is in Greenbelt, Maryland. So it's only about 5 miles down the road from College Park. I've been living in DC proper for the whole time, so enjoying city life. 2004, I took the opportunity of this being a very diverse place to work with a lot of different activities going on to build relationships and take some chances. And so, whereas I started, there's me at 15, I don't know, it's 27 in 2004, and kind of evolved through instrument technology into instrument science with my physics background, got interested in some of the management roles that I could do in parallel with my technical activities. Became a mom a couple of times along the way there, and then found myself with the opportunity to serve as deputy principal investigator for the DaVinci mission, which is not something I necessarily lobbied for or imagined myself doing, but it is one of the best things I've ever done. And it's a really, really exciting team to be a part of, and a really exciting time to be thinking about Venus science. And then now I have this official management headshot. So there you go. You can also see the progression of the gray hair. It's almost complete, that transition. So let me tell you a little bit about DaVinci. I'm going to take a sip of water. So DaVinci is a discovery class mission. That is the smallest PI-led type of mission that NASA funds. It's intended to be a little riskier than the flagship missions. It's definitely cost capped. It's definitely intended to be, a modest scope targeting, specific science questions, and DaVinci definitely does that. At the same time, this is a element mission that is going to study Venus as a system. We're going to study the clouds from above. We're going to peer through the clouds on the night side and try to look at some of the landforms on our flybys. And then we'll drop a probe through the atmosphere. We are building, though, upon a lot of hard work by a lot of really amazing team members. I'm very privileged to be part of this team and to be helping to lead this team, ranging from project managers to systems engineers, as you would imagine, instrument scientists. Our science team is incredible, financial folks, really whatever you do in life, there is a role for you at NASA, because it's really a group endeavor. I do want to point out really quickly, I think the one PSU alum is here. This is Alex Pavlov, who studied with Jim Casting a couple decades ago, and he's on our science team and is an expert in isotopes in the atmospheric chemistry of Venus. So, so really, Venus, what we're building on the legacy of exploration of Venus that was very active in the 1970s and 1980s. The Soviets sent landers to Venus. I'll show you a couple of images that came out of those missions. And NASA last sent a mission into the atmosphere called the Pioneer Venus multi-probe. So there's a large probe and several small probes that descended through the atmosphere. And despite all of that attention, there are a number of questions that remain open. And so this is from the most recent decadal survey, Planetary Science and Astrobiology Decadal Survey, that shows that our quest to understand Venus as a system continues to be relevant, because we haven't gone back. And so we have a lot of open questions about the origin of the inner solar system, about the range of possible geology throughout the solar system, how surfaces of planets like Venus are formed, and how that is expressed in the chemistry of that planet. What is the role of impacts in the early solar system to delivering materials and volatiles, as we know happened for Earth? And once a planet is formed, how does it evolve? Venus is, an example of, a planet that's been several kind of planets, we think, over the course of the 4.5 billion years that it's been around. And so, but we don't really know how that worked and how it evolved. So, so these are all questions, including the evolution of habitability of Venus, potentially over the course of its evolution as well. So, so we're very excited to be contributing to these big questions that the Planetary Decadal Survey continues to make a priority for us. And for those of us who see Venus in the sky is, often the brightest object in the sky. You may not think about how unappealing it is near the surface, because it's just so beautiful. But it's, it's enshrouded by a contiguous cloud deck. Those clouds are made out of aqueous sulfuric acid and some other things that we don't quite know, but we need to find out. Mostly carbon dioxide, with a surface temperature of 460 degrees Celsius and a surface pressure that's 92 times the pressure at sea level on Earth. Very windy in the cloud deck that kind of decays down to calm winds near the surface. And of course, that cloud deck is tens of kilometers thick. And we will be piercing that cloud deck and learning a lot about what the deep atmosphere is. So of course, these are the region, these are the regions that the Venera and Vega landers explored back in the 70s and 80s by the Soviets. They did successfully land in this incredibly harsh environment, and they did that well. What they explored were basaltic plains of Venus, which are fascinating, of course, in their own right, and expressions of pretty catastrophic volcanic resurfacing of the planet. It looks a little bit like an old parking lot, honestly, in the asphalt. And you see that, the sky is very hazy, and the light from the sun is very diffuse. And so these are all helping inform us how to design DaVinci to not only survive that environment, but also form our expectations for what we can do with our payload as we explore an entirely new region of Venus. So 80% of the surface are these basaltic plains. 20% of the surface are regions known as tesserae, singular is tessera. And we are going to be exploring a tessera region. We'll be descending over a tessera region that's very special to us at this point, called Alpha Regio. This is a characteristic of these highland regions that look different in radar. These are views of the surface of the planet that were acquired by Magellan back in the early 90s. And you can see that a lot of the planet are lowlands, some mountainous regions, and some of these like really rugged regions, tessera regions. There are hypotheses out there that suggest that the tesserae are ancient continents. That they're the oldest expressions of surface geology, and may hold the record to what Venus looked like before it became the kind of volcanic hellscape, that it is today. And so we're really excited to, for the first time, descend over this region and get the first images. Now, before Venus became what it is today, there are hypotheses out there and still an active area of research and debate, but that might suggest that these continents might have protruded out of an ocean-bearing planet right next door. And with the previous missions that explored the atmosphere of Venus, some of the measurements like the deuterium to hydrogen ratio in water are so extremely high that it's consistent with the loss of quite a lot of water from Venus. Now, how much water was lost, when it was lost, and whether Venus can be a prototype for exoplanets that we are poised to discover is some areas that DaVinci will provide insights into. So I mentioned, a watery Venus is one possibility. What we know likely is that Venus started as a magma planet, and there are two hypotheses, and we really don't have enough data yet, we think, and to differentiate between the model where Venus was always dry with maybe a steam water atmosphere, and a model where that water was condensed on the surface to form oceans and could have lubricated like some tectonic processes on the surface, akin to how Earth works. So really our goal is to differentiate between these models, and if we do determine that wet Venus was likely, at what point does this runaway greenhouse effect take over the planet? And so we're looking at origin, we're looking at evolution, and we're looking at timing. So if some of these models are correct, it's possible that our inner solar system hosted 2 or 3, if you count Mars, possible habitable ocean worlds, right in our neighborhood, close to the sun. And so this is a really profound possibility. And if you look at some of the models, it's possible that Venus, was habitable for most of the history of the solar system. So really setting a timing on when that habitability was lost is important to understanding, how what the inner solar system looked like, and what that means for the prevalence of habitable worlds in the range of possibilities for rocky planets. So this is just another view of some of the missions that came before us. Descending through the clouds is kind of hard. So, we do have the Vega and Venera landers to build upon. We have the Pioneer Venus probe that suffered, unfortunately, a clog, a droplet got stuck in the inlet to its analytical instrumentation. And so that really obscured our understanding of what the deep atmosphere is compositionally, and how things, may vary as we near the surface, and what that means for the exchange processes, not only, the chemistry that's going on in the clouds and below the clouds, but as we near the surface, there's a lot to be learned about how the rocks in the atmosphere exchange chemically. There have been a series of orbiters that have been conducting observations of the clouds from above for a good continuity in those measurements. And so that has been, really important to seeing the time variability of the clouds. But there are mysteries at the top of the cloud deck as well. We think, they're mostly sulfur dioxide clouds, but there are some components of the clouds that absorb very strongly in the ultraviolet, and we just don't know what that is. There are some hypotheses, but DaVinci is also hoping to bring some new spectroscopy capabilities that I'll show you to extend the range of what the measurements that we have of the chemistry in the upper clouds. All right, I'm sorry, somebody is chatting me. All right. Okay, so our focused discovery class mission really targets in on three major science themes. The first being the origin and evolution of the atmosphere, the composition and the interaction with the surface, and how that's expressed in present day Venus. There's I'll talk about the ocean quite a bit, but the possible ocean quite a bit, but this bullet about the rate of volcanic activity at Venus has gotten a lot more interesting in recent months, with the report of observed time variability in a pool of lava, really, in the Mont-Mons region of Venus that was reported at LPSC earlier this year. And so it looks like, at least in the Magellan era, since those were images, radar images taken in the early 90s, those two images separated by 8 months suggest that there is ongoing volcanic activity at Venus. And so that makes it even more exciting to consider what changes have occurred since those previous missions to the atmospheric composition, and what DaVinci can contribute to the understanding there. And then our third theme is about surface properties. So, we're going to bring a descent imager for the first time to Venus. And as we descend over this very special tessera region, we'll be taking descent imagery, and we'll be able to build up topography of this rugged landscape and then connect that to our regional observations from a couple of flybys that we'll do on the way. So this is the architecture of our mission. We're not that far from Venus, right? Like, we're originating from Earth, but we have some requirements on the descent phase of our mission that makes it required that we do a couple of flybys to get just to the right position, just in the right lighting conditions to be able to do that descent imagery. So we will launch in June of 2029. And our first science is just 6 months later. It's great. I'm going to tell you about the payload, but on this first flyby and on the second flyby, we'll be imaging the day side of Venus, and then I'm going to show you a video later, I think. And then we come around the night side and peer through the clouds at the thermal glow of the surface through the clouds. So we'll do that on both flyby number 1, which is 6 months after launch, and then again on flyby number 2, which is 9 months later. And then just in a couple of months after that, in June of 2031, our carrier relay imaging spacecraft, which our PI Jim Garvin likes to call Chris, because there's not enough Chris's in the world, will release our probe flight system, which has an aeroshell encapsulating the probe. And then over 2 days, that aeroshell will drift away from the spacecraft and then descend through the atmosphere on a parachute for part of the time. There's another way to look at this, the way engineers look at things. It's very linear. And so this just describes what I showed you. There is quite a lot of work to be done to document the science that we promise to deliver to NASA, and one of the key work elements that we've been putting a lot of effort into in these early stages has been our PLRA, our level 1 requirements. So these are really what we promise to do with the mission, the science that we promise to deliver to the NASA agency. And this is kind of it distilled, but what it shows you is that, you know, we think lofty science questions that are very important to humanity. And then we map that down to the way our payload works. And I'm going to describe the payload here in a second. And make sure that we can answer all of these questions and we understand which instrument is doing what and how the instrument has to operate to answer those questions. And so we have 7 instruments, and I'm going to go through them in a little bit. All right, this starts a little bit of a description of the payload. Again, this is our carrier relay imaging spacecraft. It's got 4 camera heads that I'll talk about in a little bit. The Venus imaging system for observational reconnaissance is VISOR. And then we have our tech demo, our technology demonstration QVIS, which is the compact ultraviolet to visible imaging spectrometer. It's a completely new type of spectrometer that I'll talk about in just a few minutes. On the descent sphere that separates and goes into the atmosphere, we have 5 instruments. We have the Venus mass spectrometer, I should be telling you who's building what. No, you'll see that later. I'll tell you in a minute. We have the Venus tunable laser spectrometer. These 2 instruments have been operating on Mars at Gale Crater for over a decade now, and making really important discoveries about the chemistry and the isotopic composition of surface materials in the atmospheric variability with seasons on Mars. And so we bring these superstars back together to make awesome discoveries at Venus. We have VASI, which is our Venus atmospheric structure investigation. VenDI is our Venus descent imager. Everything has to start with a V except for QVIS apparently. And then VFOX is a student collaboration experiment, and that is going to measure in the deepest regions of the atmosphere the oxygen partial pressure. All right. Okay, this is just a pretty picture. And so is this. So this is what the descent sphere looks like, all packaged together. It shows a little bit of the detail of the instrumentation. So we have a sapphire window at the bottom. The Venus descent imager peers through that window as we're descending. We're gonna spin the descent sphere so that we stabilize what we're looking at. And our analytical instruments are VMS and VTLS are on this forward deck. They're mounted underneath. There are some inlet ports to get the gas into these analytical instruments. Over here is VASI, sits inside and outside the probe to be able to measure the atmospheric structure. And then all of our electronics are kind of held here in the middle. So, you know, you ask, well, how are you going to prepare these instruments that were kind of built for Mars and other places to go into this harsh Venus atmosphere? And the answer is you just like put a thermos around them, which is really what our descent sphere is. It's titanium. It's intended to isolate thermally and in pressure the instruments from the Venus atmosphere. All right. Oh, okay. So this is my fun with animations in PowerPoint. Okay, so we're going to be the descent sphere. I'm going to walk you through how the operations are going to work. So starting in the upper cloud deck at somewhere around 60 kilometers off the surface, we are going to start to do our analysis of the chemistry of the Venus atmosphere. So we'll start to measure with our mass spectrometer, measure with our tunable laser spectrometer to look at composition and this key isotope ratio of deuterium to hydrogen in water and some of the other isotope ratios. Now, as we pass through the clouds, VMS goes to work in measuring the complete suite of noble gases. And I'll tell you in a minute why that's so important. As we emerge from the clouds, we start to take images, and we continue snapping images all the way to the near surface. And then we take altitude resolved measurements of the chemistry and the atmospheric structure all the way down. And then in the deep atmosphere, we get closer than any mission has done before in measuring the composition of the atmosphere and how that relates to the observations that we're making of the surface. These paired images of VenDI are going to be reconstructed into topography of this unique region, this tessera region. Okay, so let me walk you through now how we take our measurements and translate them into, answering this key question about how much water Venus had, where it originated from and what happened to it. So we're really trying to understand all of the sources and all of the loss mechanisms of water with this comprehensive suite of instrumentation. So to understand the origins of the atmosphere and the role of delivery of volatiles by impactors, this traces to our noble gases and isotopic signatures suite. This is highlights the importance of xenon. Of course, our previous measurements give us, almost the whole suite of noble gases, but we did not get xenon. And so from previous data, if you look at the kind of behavior of this curve, how the signatures of the noble gases look for Earth and Mars, they kind of follow the same curve. But for Venus, a big question is left open. Did Venus follow the same, origin path? Or is it on a different evolution pathway to preserve a more primordial atmosphere? And so we don't know with existing data. The krypton data bars are too large, and we don't have any xenon data. So xenon is incredibly important to understanding how Venus compares in its origin story compared to Earth and Mars. So that's a oversimplification of how we learn about the origins of the planet and what happened in early phases. Now we have to think about degassing. So what water was indigenous to Venus, and how did it degas over time? So we're going to look at the dependence of how the noble gases can really provide us insights into the timing of the onset of volcanism. So we'll look at the differences between expressions of helium, argon, and xenon to be able to put some time constraints on the potential different models of whether the volcanic resurfacing was recent, we should be enriched in helium compared to xenon, or if the degassing happened a long time ago, then xenon would be preferentially more preserved. All right. Okay, so as I mentioned, the Venus mass spectrometer, it's got all of the capabilities of your traditional mass spectrometer. It takes an atmosphere, it tells you what it's made out of up to a point, as long as it makes it through the system. But it's got a special mode on it, VMS does, compared to compared to SAM and the neutral gas and ion mass spectrometer on MAVEN that's still orbiting around Mars. VMS has a lot of the same internal components. It does not have a gas chromatography mode, however, and it has a special noble gas enrichment mode. So this is really built on what SAM has done on Mars and what we've learned from the Galileo probe mass spectrometer that went to Jupiter decades ago. And so what happens as we're passing through the upper part of the atmosphere is that VMS grabs a sample through its new and improved inlet technology that will not clog in the clouds, and it'll spend the time as we go through the clouds running a sequence of enrichments, or actually an enrichment step that will allow us to measure the complete suite of noble gases, which is very exciting. So that's how the part of the payload maps to some of these elements of this fundamental question about water on Venus. We're also going to confirm previous measurements of deuterium to hydrogen in water to talk about and to confirm and look for gradients in how that tracer of atmospheric loss is expressed throughout the column of the atmosphere. So in previous measurements made by Pioneer Venus and also can be done remotely, it's been pretty well confirmed that the D to H ratio is off the charts. So deuterium much more prevalent than hydrogen. And so this is consistent with major loss of a lot of water. There are some suggestions that previous measurements have seen gradients. It's not really expected. So we will make those measurements with the Venus tunable laser spectrometer. We'll have up to 10 altitude resolved measurements of D to H in water from above the clouds to just before we hit the surface. And VTLS is built out at JPL. Led by Chris Webster with his deputy Amy Hoffman. And it's got 3 laser channels that will allow us to measure D to H in water and oxygen isotopes in water, carbon isotopes in CO2, triple sulfur isotopes in SO2, and triple sulfur isotopes in OCS. And so this is, again, a well-proven technology, and we're excited about making these definitive measurements in the deep atmosphere. This is a Harriet cell type of instrument, and you can see the type of data that will be produced and the laser wavelengths that will be used there to zero in on very high precision on these isotope ratios, and really a very sensitive instrument to look at parts per billion type levels of these compounds in the atmosphere. All right, so this kind of shows how we use the upper atmosphere, part of the sequence, and the lower atmosphere part of the sequence to really take regular cadence of compositional measurements of the atmosphere with VMS and with VTLS. VTLS takes a bit more time to integrate, and so we'll get fewer, but we still get a really good gradient understanding of the gradients, and we can increase the cadence of those measurements near the surface to look for gradients of this chemistry near the surface. These are some early, these are some predictions of what the atmospheric variability looks like, but these are still, unconstrained really by measurements. So we're very pleased on DaVinci to be able to provide a new set of high precision measurements to really fill in our understanding here. We also carry the Venus atmospheric structure investigation. This is led by Ralph Lorenz at APL in Maryland also, and his deputy is at JPL, David Atkinson. This is really a collection of kind of off-the-shelf components that should work at Venus, and we'll measure temperature and pressure, acceleration of the probe to reproduce the trajectory of the descent and the local winds. And all of these physical properties of the atmosphere together will provide the context that is really important to us for us to be able to put into context the chemical measurements and fully interpret the data set that we will be acquiring here. There have been pressure temperature profiles acquired for Venus, but the resolution has been relatively low, and it has not been correlated with the compositional profile. So this is another first For DAVINCI, we're looking to get 15-meter resolution in these measurements as we descend through the atmosphere. And we'll look for things that have been recently predicted, like this differentiation in the lower atmosphere and potential variability of gravitationally separated nitrogen from CO2, which would be pretty weird and shows some interesting layering in the atmosphere that is not seen on Earth. All right, let me spend a moment to complement these compositional measurements and the atmospheric structure measurements. We're going to take this little sensor that'll be built and tested by students. The students will be supervised by Noam Eisenberg and Sarah Hurst, and David Kramer are the academic leads. So this is our student collaboration experiment. At least 120 students will be involved in the building of this little oxygen fugacity sensor. And as you can tell, Noam Eisenberg is real talented at logos. So if you ever need a logo, I would really suggest that you reach out to him. Also, if you need a DaVinci sticker, he's a good source. I will have some for you next time I see you all, I promise. So this is a really exciting way to bring students into the process, allow students to see, all the different phases of how a flight project is built and implemented and operated. And so we're excited about the students there. The last little piece in this profound question about a watery Venus is about water-rock interactions. So, so we've been talking about atmospheric composition and signatures so far, but we also carry our Venus descent imager that I've mentioned before, and I'll just introduce also VISOR here because both imagers are being built by Malin Space Science Systems. And the lead here is Mike Revine, and we have Brent Boss from Goddard intimately involved as someone who's an expert in camera technology. So let me talk about VenDI because this is the one that will really tie the local observations of rock type to potentially watery Venus. So VenDI, if you care about CAD models, is what it looks like. And it's got two, I should mention, it's got two band passes. It's got a broad band and a narrow band pass. And by ratioing those, the reflection of what the surface looks like in these bands, we're looking to discriminate between rock type. So this type of descent imaging, this is not Venus, obviously, has been demonstrated on Mars and makes for a pretty exciting sequence of tracking the landing of, this is, of course, Gale Crater. So this is the Curiosity rover landing. And so it just shows how progressively you can get this regional scale and then really zero in on sub-meter scale imaging to get human scales that are understandable to our eye. And so if we were to imagine, if we were to, as artists, imagine what the tessera region will look like as we descend over this ellipse and this really interesting alpha regio region, we're going to be looking at those ratios between the broadband and narrowband in the descent imager and looking to discriminate between something granitic that has been formed through weathering and interactions between the water and the rock and kind of the basaltic, the volcanic background. And so we're really excited about this additional piece of the puzzle here. And if we, just to relate it back to geology, mafic rocks are low reflectance and high emissivity, so they're dark. They're the basaltic rocks originating from the melting of the mantle, but felsic rocks, higher reflectance, brighter rocks, really, with analogy to what we understand about geology at Earth, would be formed through this processing with crustal water and the interaction between the water and the rock in this type of cycling, lithosphere cycling. So this gives you an idea of how we plan to ratio those narrow to broadband and the kind of discrimination that we can expect between basalt type rocks and granitic type rocks. And so a lot of modeling is going in to inform our expectations and to show that the techniques that we're using are adequate to make these discriminations. It's a little tricky because the atmosphere will produce some blur, but with analogies to the moon, there are regions on the moon that kind of show these two rock types. And so with lunar reconnaissance orbiter camera, as an analogy, we've kind of shown that the technique should give us the data that we need. And so, we expect to with the visible imagery and the structure from motion as we're descending over this region, we expect to be able to build up digital elevation models for the first ever topography of this tessera region. So we're very excited about that. That's going to be complemented by our regional imagery that will be enabled by VISOR. So VISOR, again, are 4 camera heads on the relay imaging spacecraft. And so we're going to be able to relate this kind of ground truth near the tessera region back up to the IR imagery that we'll get on the night side to be able to peer through the clouds and draw some generalizations about alpha regio compared to the other tessera regions that we see on the surface. And then on the day side in the ultraviolet, we'll image the clouds and we'll look at cloud motions and we will correlate those. Well, this is an example of what we'll see on the day side with this characteristic, shape of the in the UV of the cloud structure on Venus, and on the night side, peering through the clouds as best we can, discriminating between bright and dark regions with the infrared to correlate with different rock type again. So VISOR and VenDI really work together, and this is just depicting, the kind of field of view of VenDI as we descend compared to the field of view and resolution of VISOR to show how we'll really connect the local data to our flyby imagery. So taken together with the compositional measurements, the rock type measurements, adding a new element. We're really excited about DAVINCI providing a new view of Venus and exploring the extent of what habitability may mean for the inner solar system over time. All right, so let me mention here our technology demonstration. This is QVIS, or compact UV to visible imaging spectrometer. So it's going to get again at the composition of the clouds. Now the clouds have some dark regions that are different from the sulfuric acid dominated chemistry that we know about the clouds, and so QVIS will reach farther into the ultraviolet to provide some new insights into potential composition of this constituent of the cloud deck. That is, what we call the mystery absorber, the UV absorber. So it just it's undetermined right now, but people have hypothesized that it may be one of a couple of different sulfur compounds, or a chloride bearing compound, or maybe an iron chloride. So there are a lot of candidates out there, and we just need more data to be able to discriminate. So QVIS, being hyperspectral, will get over a smaller field of view than VenDI, but will get in its field of view a spectrum that's correlated to each of the pixels here. So we'll really be able to just, tease out what those spectral features are for the dark UV absorbing regions relative to the bright regions. All right, so we're excited about the era of the James Webb Space Telescope. Many people have observed that Venus, maybe the archetypical Venus type exoplanet. And so it's really important when we're making predictions about what the planetary characteristics are of exoplanets that we're poised to discover. So it's really important to understand Venus and be able to draw the right appropriate conclusions about how Venus works and what that means for exoplanets like Venus. And so with JWST, the Venus zone of the solar system is more favorable to JWST is kind of biased to this region. So we think the timing is really excellent to provide the in situ measurements that will feed into modeling of the atmosphere and really enhance our understanding of how these exoplanets work and what it means for planetary habitability over space and time. So just nearing my conclusion here, Venus very much deserves to be treated as a system. We have a lot of the pieces in place, but with DAVINCI, we're very excited about connecting the remote sensing observations to the in situ observations and considering how Venus works as a planet, and will be complemented by some of the upcoming radar missions, mapping missions like Veritas and Envision that will be very complementary to the science that we're doing. And so, Venus has been neglected for several decades. In situ Venus, the atmosphere of Venus has been neglected for a long time. And so we're very pleased to be the team to be bringing NASA back into the atmosphere. I'm going to show a real quick video if we have time. And I can, you've seen a lot of this, but our videographers worked really hard on it. So I forgot to mention that our CRIS spacecraft will be built by Lockheed Martin, and we have partners across the country, and we have science co-investigators also from Europe. So our team is geographically widespread, but we've really been building a good team environment. So this is flyby number one, where where VISOR and QVIS will look at the day side of the clouds, and as we kind of fly by the planet, then we get to look at the night side and collect images in the near infrared band passes. And build up an understanding of how eventually our alpha regio observations will connect more generally to tesserae at Venus. And then on what is really our third gravity assist, the probe enters the atmosphere. The parachute deploys, the aeroshell flies away, and we start our atmospheric structure investigation measurements with VASI while we're still on the parachute. We're definitely in the clouds here, so doing our noble gas analysis. We're starting to look at D to H ratio with VTLS. You notice we're spinning to stabilize ourselves so we could take measurements, and we think that this regular altitude resolved sequence of measurements will help us elucidate the chemical cycles that are at work in the Venus atmosphere. And then as we descend, now what I didn't say, but you're all thinking, what happens when we land? We don't have to survive landing. So we will take all that imagery, we'll take all of the analytical data, and we will transmit it all back up to the CRIS in the very moments before we hit the surface, so that we don't require the probe to land. This is a feature of Discovery class missions. You don't require what you don't have to answer your science goals. And so you can see here, it's probably a very dramatic landing, but we don't show it in the video. And there it is on the surface. And we have now unlocked in 2031 all of Venus's secrets about its oceans or not. And in the era of just exploding, discoveries of exoplanets, we're playing a role in how to interpret that. And then Jim Garvin is really dedicated to the connection between the innovation and art of Leonardo da Vinci and our namesake. And so that was Florence. That was a picture of Florence at the end there. So you can imagine Da Vinci being very proud of us and our mission.